I've started the recording. So this is your lecture for Design 330. It's week 7, which is, and we're on Thursday, March 4th. And we're working on bills of materials and things like that. But we're also going to just barely start into talking about manufacturing processes. And we'll be continuing this next week and the following week. So this is a very kind of superficial view of these operations and these machines. And after 3 weeks of just talking about them, you'll have a little bit more of an idea once we get into actually doing the building where these machines will be. So, um, I'm going to do a few things today besides, well, I'll go in this order. We'll talk about milling, turning, and 3D printing. And then we'll talk about the milling sim. Now, so far, Wasan is the only one who has a milling sim put up. And it's going to be hard for you guys to do your milling sim collaboration if nobody is posting stuff for you to collaborate with. So you might um, uh, just send a message out to everybody that says, folks, I'm waiting. I need your work. Please do it soon. And it's a small part of the whole thing, but it's really an integral key part. So there we go. All right, so let's take a look. First of all, I've given you some really nice little YouTubes. I picked these ones out. What did you think of these ones, Alex? Did you like these ones? Okay. Yeah, and those were from SME, I think. That's the organization you're part of, right? So so you can let them know. Yeah, my professor even used your stuff. They're just clean and nice. These ones are just like they're basic, they're clean, they're nice. They give you the overall, and they're short and direct. So I like these ones. The 3D printing one, um, there's all the ads. Bank. So they're using our little 3D printers in our lab are extrusion style. This is additive where you put down a layer and you fuse it and put down another layer and fuse it. And I'll tell you, this is so much more precise and so much more cool than the ones we've got. And you can really do cool, neat stuff with it. So we'll talk about that a little bit. It's just an amazing concept of being able to control our materials so well, and so that's kind of a neat thing. And if you're interested, Farhad Gadamli was our very first 3D. He wasn't even an intern. We didn't have the design hub when he was with us, but he was part of the engineering club and Design Tech had bought some 3D printers. And so he came over and just fell in love with 3D printing. He was an engineering student. He went to UC Davis and got his bachelor's degree and then got his master's degree in additive manufacturing. And he's worked for some really cool companies. And right now, he works for a company that makes the materials. He got his master's degree is in material science. He actually works for a company that makes the materials that 3D printers use. Um, oh, cool. So Alex, what did he do that through SME? Is right, right. Yeah, oh that's really cool. Yeah, if you could send it to me, just a link to it. That would be really cool. I mean, I'll tell you, that guy, he's smart, isn't he? He's like, wow. He would talk about stuff, and I'd be going, Farhad, bring it back down to earth, man. you know, yeah. But it's really cool, right? And he's an ARC graduate, so um, and he got his start in 3D printing. I'll have to try to find the darn thing. It's around my house somewhere. I had this wooden printer bot that was held together literally with wire ties. Bearings were held in with wire ties and everything. And he was able to make stuff on that thing. Uh, so I mean, he's really one of the forefront guys in it. So that's really cool that you got to see a seminar by him. And you can give him a shout out if you want. Tell him, hey, my professor was talking about you in class yesterday. That's really cool. That's neat. Anyway, so we'll talk about those things and we'll go about the milling sim, or the milling sim. But these are kind of cool. But what I want to do is look at how you'll put together your work. And you've seen me do this before. How do I take notes for these things that are kind of like research and putting my information together? And the big takeaway here is that you want to be well read. You just get in and spend your time finding stuff out, reading stuff. Hopefully you're on sites that, we don't need the QAnon uh, milling thing and stuff like that. But Wikipedia is pretty standard. And SME and Alex, you probably got some really good ins on these things. But just get some good basics down from web research. And this page, I'm hoping, will take you about half an hour plus the milling sim. The milling sim is a little bit longer. So I spent about half an hour, and this is what I got. Okay, just looking around. Now, I kind of know this stuff already. I could have just written it down, but I spent my time finding stuff. So I found this thing, and look, I've even got, I think I can link to it. I have to put that on the back. Hold on a sec. There we go. So I found where that was, and I even, just to show that you could take your time, I found that I'm able to use that because the person tells me so. Okay. I get to do all these usages that I'm allowed to do. Okay, right here. I can share it, I can remix it. I just have to attribute and I can share it alike. So that's kind of cool. If you feel like doing that, it's not required. Um, but let's take a look at this. So I just found some information. Here's a quick description of milling. Rotary cutters. Rotary cutters, what are those? These are rotary cutters. And I find out that they have sharp flutes. Those are those twisty little sharp edges. Uh, cut, not cout, cut into it that cuts the metal off as it rotates. And that was from msdirect.com. And it removes metals from a chunk that's bigger than my final intended piece. So I put a big chunk on there and then I use it. Okay. And so that's all of interest. Now, one of the things um, that's important to note is that in our sim, okay, if you look at this, well, let me zoom in on this again. This is where the tool cutter goes, right here. You just plop it in there, and then this rotates it. This machining head rotates it. And it rotates depending on what speed you turn the motor and what belts and everything. It gets really moving and grooving. It's fast. And see this little digital panel up here? that gives you all the information that comes up on our panel. X position, Y position, Z position, some other stuff, and you can move stuff. You can move these handles. Now, what's different about this than our simulation is the milling cutter stays stationary and you move the part underneath it. So you turn this handle and it moves this way and it moves this way. And this bed moves up and down. So in real life, in most mills, not all mills, um, in most mills, the bed moves and the head stays still. But that's not a given fact. But I want you to know that from this. In our simulation, the tool, this whole thing is moving all over the place and the block is staying still. And they make them like that, so that's okay. That is a Bridgeport. Isn't that cool? Although this one's been remade by somebody else with the motor. But yeah, that looks exactly like the one that you put in the room, right? So Alex has been working on, or Wasan has been working on filling up our machine shop for us. So I just made some notes here, and let's take a look at these. This is what an end mill actually looks like. Okay. And the gold coating is a type of anodize that makes it very, very hard and lubricious. That means that it slides really easily. Um, and the tool steel itself that this is made out of is very, very hard and durable. And so it's called tool steel, which is much harder than most of the steels that you'll be cutting. And that's cool. But you can imagine it's a fixed diameter. Okay. That's one of the things about milling. You pretty much get a fixed diameter of your end mill. So that sets how small little corners can be and how much you can pull off. Okay. Now you can make fancy mills with different end configurations and things like that. I actually worked at a company that made lathe tool bits, form tools. So there's a lot you can do with these, but in general, it's just a cylinder that's spinning. Okay, so that's my description of milling, and I'll use that information in some fashion to describe milling. And I actually do this on my file when I use something like this. Now let's talk about the advantages of milling. What is milling used for? Well, this one I took from Wikipedia, that same Wikipedia. Small individual parts to large heavy duty gang milling operations. So I've done manufacturing work where we'll set up 50 parts on a big mill and we'll do the same thing to every single one of those parts and we'll program the CNC so that there's not very much loading and unloading and loading and unloading and waiting and stopping. And so you can gang parts together to make more than one part at once. You can make custom parts, very, very precise tolerances. I think we had one R&D machinist that would really, really, really understood his mill and could regularly get down to half a thousandths of an inch and really with care get 1/10,000ths of an inch. And we did have parts at Tri-Tool that really needed that. And so you can do custom machining, precise machining, huge parts. One mill that I worked with at Wemco was about 25 feet long, and it could take a part that was about 8 feet tall, and it was just huge. And we actually put giant tanks, like not like a boom boom tank, but a tank for working with slurries. And we had to get certain hole patterns for the motor mounts. And so we just stick that whole big tank up there, and then we'd machine the top flat. So that's really cool. You can do a lot of different milling can be done because you're rotating the tool, not the part. So there's lots and lots of milling machines. We made a portable milling machine for the Navy that would fix and remill the heads to their nuclear reactors for their submarines. And it was portable, and you would just move this thing into place, and then it would have the milling function work. It's easy to do exactly the same thing over and over again. It's very repeatable, easy to control the motion. You're just kind of like turning a good handle, and you can mill just about every material. You can mill you can mill glass and plastic and metals and wood. You can even mill rocks and concrete if you want. And literally almost unlimited size and weight. Now, I don't think we've made mills for whole buildings, but we're probably getting there with the 3D printing operations. And you can vary the process if needed. Automated, simple, external. So now look, here's the big thing. It only does external. Yeah, you can do glass. Of course, you need to have really good support because you can't vibrate, and you have to have an excellent cutter. So they have, well, you can imagine it's like diamond dust cutters where the little diamond bits go. Um, so that's kind of that is, yeah, glass is really cool. Um, so now here's the main takeaway though. It's advantageous for external features. You can't do inside stuff very well. It's stuff you can reach from the outside. Okay. And it's best um, for one direction. That's the best. So let's see what it's not very good at. And let me put a little shape around it. It's not very good at deep parts. In other words, if you let's take a look at this thing, you can imagine this is a big old clunky thing. So I can't get very deep down into a part without having an end mill that sticks out a long way. Well, you wouldn't think it, but the side loads are pretty heavy when you're cutting metals. And these end mills look like they're pretty strong, but they can bend too. And you can just be off on your tolerances and everything. So the deeper a part gets, the harder it is to end mill it. Okay, so that's a thing that doesn't work all that great. The mill needs to be really long, or you have to have a big open area where you can put a really fat end mill down there. Internal spaces are hard or impossible to make, right? I mean, I have to get to it from the top. And so if there's weird stuff inside of it at weird angles that I can't get to, it's hard. It's hard to do. So that's a thing that's hard. Sharp internal corners are hard or impossible to make because I have a round cutter. So how do I end mill something that's got a sharp corner? Now, I'll tell you, there's some incredibly smart, ingenious tools that can do it. So Alex, you might, and it's called mill broaching. And if you're interested out, you can ask some of your SME people if they've ever done mill broaching. It's kind of goofy and it's not really high production. And it's probably quicker and easier to do other stuff like EDM or electro discharge machining or something. But sharp corners are a problem. But guess what? Sharp corners cause problems in design with forces and stress anyway. And so many designers stay away from sharp corners so you don't have to worry about it. But they're bad for sharp internal corners. Holes in multiple directions. So I can drill holes and make holes up and down, but to go sideways holes, I have to take the part off and flip it and then start going up and down. And every time you flip it, you might lose your 0 point unless you've done some fancy fixtures and things like that. So holes from multiple directions. Now, look, they've actually got mills, multi-head mills that come in from all angles. And now CNC, you put a turret on here that turns the part for you. And so some of these are not really problems, but they make life more difficult. Certainly not impossible. Now with what they call a 5-axis mill that can turn the part anywhere and turn the head anywhere, you can make just about anything. So long as the internals aren't too goofy. Okay? So that's sort of how you would do one of these pages. And you would do the same thing on turning and just go look it up. Turning is a lathe. So it's going to mostly make round products. Although nowadays they've got such cool, multi-tool lathe mill combinations. It's really wild now what they've got. Um, but you'll do the same thing. Figure out what turning means. What are some of the advantages? What are some of the disadvantages? And now we want to talk about compare cost saving material versus saving time. And that should be a very simple table. I just want something super simple there. So I'm going to do one right now. I'm going to, I just did that wrong here. Time, costs. So time, costs, money. Okay, there's setup, machining, cleaning, and inspection. Okay. And so that's money. Okay. And we measure in hours. Time costs money. Material costs money. In turning what they call the blank is the material cost. So that's the bar, the round bar cost. Okay, so whenever you do a manufacturing, you have to balance the time cost versus the material cost. So how do you do that? Let me just go time. So the more you have to machine something, the more it costs. If you're machining, okay, has a lot of material to remove, it's going to cost more. Okay, so sometimes even if a piece of material is very expensive, if I don't have to do much to it, it can come out better. So what are your time costs? Okay, it's your dollars per hour times how many hours. So you can see you want the most efficient set of operations possible. Dollars per hour times how many hours. Material is usually either in dollars per volume times the volume you start with, or it's dollars per pound. And of course, times pounds you start with. So now look, if I make a very lightweight part, let's go look at it from the point of view of turning an object. If I make a very lightweight part, but I start with a chunk of material and I machine it a lot to make it lightweight, this is the volume you start with, not the volume you end with. So I used extra time and I didn't save myself any money by making it light. So if you make a light part from a large blank, you have spent more money than leaving it a large part. That's sort of what I'm looking at. That's the comparison. That's what I mean by compare the cost. Here's how I measure time costs. Here's how I measure material costs. I need to know those two things so that if I have many people say, well, make your part lightweight, you'll save money. No, you won't. It depends on what you started with. Now, that's not the case when you talk about 3D printing because you only pay for the cost of material that you've used on the part. Same way with casting, because you reuse the unused filament or powder. It gets reused, recycled. And so when you look at this, compare the cost, you've got time, but here you're going to have to talk about really what. So, I want to do one other thing. When I talk about time, I just want you to think about labor time. That's the time a person is actually there at the machine making the part. Because nowadays with CNC, and nowadays since the 70s, right, you can load up a part and start the machine and you can walk away and do something else. So the labor time might be 10 minutes and the actual time, then the machine might run for an hour. So the person goes and does the setup of the next machine and the cleaning and the inspection. And this person can maybe run 4 machines at once. Okay. So there's labor time spent and actual time spent. And most accountants make you keep track of both. Oh, my labor spent 10 minutes, but I ran the machine for an hour. Why would they need to keep track of both of those things? Any ideas? Okay, well, I'll give you a hint here. So labor time has to do with paying people because you're not going to pay the person while the machine is running and doesn't need the person there. So labor time is really this person's deliverables, you know, how many they can produce per day or per hour. So that's a part of it, Alex, and we'll talk about that in just a sec. But the labor time is how much you pay a person for doing the person's job, which can be this and this and this and this. Actual time spent, if you think about it, very few companies, these machines are expensive. Even one of these old mills like this is probably $2,000 or $3,000 to buy an old one like this. A CNC mill um, might cost you $20,000. Well, most companies don't have $20,000 to plunk down. So they go, all right, we're going to use it 20 hours a day, um, 295 days out of the year, and blah, blah, blah. So while it's running, we're gonna count $50 an hour to pay this off in a year and a half. So they just go through these calculations and then they're making an expectation that it's being run. So so for a part, you have to know how much time is being spent so they can take that $50 an hour they're going to charge and apply it to that part. And maybe that part is not an hour even. Maybe it's zero point 0.1 hour. So it would cost $5 of machine time. And maybe it was only 10 or 15 minutes of not even that much. Maybe it was only a minute of the labor time. And they'll use, but labor time isn't $50 an hour. They're going to charge that at 25 an hour because they're going to pay the person 20 an hour and they want 5 an hour for insurance and all that other kind of stuff. So these two things, you don't have to know the ins and outs of the accounting, but you have to know that they're going to keep track of two different times. How much time the person spends and how much time the machine spends, actually spent. There. And then they're going to come out to some number for the cost for labor costs for that thing. And then they're going to figure out, right, the material cost. Now, there's also an ability to recycle and things like that, but we're not going to worry about that. Okay. And so there's two parts to this. And what you're going to find if you just do so, Wasan, you could use your part that you made in your milling sim, and you could go, okay, I just made a chunk of 4x4 by 1/2 aluminum. That cost me, I don't know, $16. And you spent 4 hours machining it at $20 to $80. So you could run a comparison, right? You could run a comparison. So that's what I'm looking for here. And it doesn't have to be in a chart, it doesn't have to be anything. It's just you can just start putting together the things and say material costs money. It's like this, like this, like this. In material, we talk about dollars per volume or dollars per pound. In time, we talk about dollars per hour. And there's two ways of doing it. And then you could make some conclusions, but maybe not too many. Okay? And then if you want to, you could compare it on your sim, because it really doesn't apply just to turning, it applies to the other. Now on 3D printing, you'll be able to look at these things online, compare the cost of saving material or saving time. And again, what does it mean to save material? Obviously, you would want your material to be as close to your final size as possible, because then you don't have to machine it as much. But saving material doesn't mean making it lightweight. But in 3D printing, saving material does mean use the minimum amount of material, because it does mean saving time. And so you can do that same type of comparison here. Why do I have 3D printing on this thing twice? I don't know why this one's on here. Delete. There we go. Okay, cool. Now, any questions on all that? And so Alex also put down, you need to know how many they can produce per day or per hour. So that goes for all three of these when you're talking about the comparison. But that's really in your production control. So your time, that's not really a cost. It's just that's more of a capacity planning. Okay. And you're right. If you think you're going to make 100 of these things and you've got one machinist and it takes an hour, then you're going to know that it's going to take them 2.5 weeks to make those 100 of them, because that's 100 hours. Um, so, yeah. So it's also part of production planning. Okay. Let's look at the sim now. So this is what you're hoping to make. Okay, you're hoping to make this thing. And this thing's a 25 millimeter mill, a 20 millimeter mill, and a 5 millimeter mill, I think, is how that goes. And your goal is to try to make this. And what I suggested is you start in the center and make that, and then figure out where to go from there. And I'll do a video of this. I think I've got some time this afternoon or this evening. I'll try to make a video of me trying to do this too. But once you've got this, you're supposed to put it in the discussion. And lo and behold, oh, I see two of them in here. Oh, I think one of them's mine. I see that Wasan put hers in. And here it is. There it is. That's cool. Well, it's obviously the right shape and the right contour, and you went through all the stuff. And so then the next question is, how do I work with it? So I'm going to show you how I put this in and worked with it. I went in and I took that and I copied it and I put it into AutoCAD and I traced it. So let me show you how I did that. Now here's the tricky part. What am I going to use to scale this to get it right? Well, I'm pretty sure that this is the 25 millimeter. So if I go 25 divided by 25.4. That should be 0.984 across that hole. So I'm going to make a line. Point 984 long. And I could even get it a little closer. I could go 98425, but 0.984. Or was that a 20 millimeter? Now I have to go back and look. Was that a 20 or a 25? No, that was supposed to be 0.984. So I'm gonna guess that that was made at 0.984. So now I'll do my align command. ALIGN. Align my object. Enter. And I'm going to do the best I can. And I'm going to pick the middle of the black line as best I can. Put it there. And the middle of, I see some pixelization, so I'll get sort of to the middle of that. There. And yes, so there we go. Now I've got this thing. I think I've got this scale. So now I'm going to try to draw it. So the first thing I'm going to do is try to draw my circle. And then I'm gonna try to draw my circle up here. I don't know exactly. Maybe I'll mirror it, hoping that she got that kind of mirrored. See how I'm tracing it? Actually, I'll just copy it. That looks pretty good, and it looks like you got it right on the same center line. So then I can come from its quadrant out and the quadrant up. So how you trace it does have a little bit to do with how you think the part was done. And now I'll go from the nearest point. And the nearest. And I'll just fill it. I could have trimmed also. There. So now, oh, and I need this hole. I'm going to do a hole 2-point. I'm off a little bit on that. And I'll do the same thing here. I'll do a 2-point hole. Well, no, this one I've got a center point. And this one I don't. So I'll do a hole 2-point. There. Now I think I have a good reproduction of the part. So there's a little bit of work to be done, but I think it's cool that you're able to use AutoCAD to do that. Whoops. That needs to be the trim function, right? Now I'm ready to measure and to do my job. So I'm pretty sure that this was called out as center line. So I can just start doing my dimensions now. So I can measure that one, and I can measure, I think those were two of the measurements I was supposed to take. And there were some other measurements that I was supposed to take. Okay. And so now the last little part is checking to see if it's right. Okay. So I'll need to go back and look at my drawing. This was supposed to be 1.250. 1.250 plus or minus 10. 1.250 minus 0.010. 1.2. Well, that one's pretty close. That it's technically it's out, but I'm going to round it up. So it's supposed to be like 1.24. So this one, I would go make green. I'll make that green. Why didn't that click over? That's why. There it goes. And this one isn't quite right, so I'll make it red. And then this is supposed to be 1.75 plus or minus 0.03. So 1.75 minus 0.03, 1.72. Oh, it made it. Look at that. That one's right in there. Green. But this one was supposed to be the same. So 1.75 plus 0.03. 1.7. Nope, that one's too big. So that's what I want you to do to somebody's. Yeah, no, and this is not easy to do. That's why we're practicing. And that's why I want somebody to have to go through also and figure this out. Now let's take a look at this diameter. This diameter is going to be, of course, exactly correct because that's what I scaled it to. Now it could be that I scaled it to the wrong thing. 0.2006. What was that one supposed to be? 0.197. 0.197. 0.197 plus 0.010. 0.207. I think you nailed it. Yep. Look at that one. That one's right in there. So this is my key to having you do an inspection drawing of that. And then I think there should be a center mark here and here, and there was a dimension to the center mark, right? One point 2.313. And what was it supposed to be? Whoop, did the wrong thing there. 1.232 plus 0.010. 1.232 plus 0.010. 1.242 is my limit. Oh, nailed it. Wow, you nailed that one. That one is really, really like, there it goes. Click on it again. All right. So there we go. That is how you're supposed to do the simulation. And so this is going to take you a while too, right? It's going to take you 15, 20 minutes to do one. If you only get one done, that's good. But it's really important to me that yeah, no, you did a great job with this. And this is not easy, particularly when we don't have a real mill to work with. But just think of if I had to buy all the material and all that kind of stuff, this is a much better way to do it. And it's giving you a concept. People go, oh, yeah, and I'll just put it on the CNC mill and it'll go and it'll be fine. And it'll take 5 minutes. And no, it still takes time to do. Um, my hope is that by the end of the semester, you can give people target points to go to and make like a CNC cheat code. So start here with this size mill, go to this coordinate point, then go to this coordinate point, then go to this coordinate point, then come back to this coordinate point, change your mill, and go up to this coordinate point and go to this coordinate point. So see how if somebody told you the coordinate points, this would take maybe 5 or 10 minutes, right? So we'll be looking for that. I don't think we'll do that next week, but we'll do that before we're done. So Alex, you're gonna learn the rudiments of G code and CNC coding. Is that cool? Yep. Right. And how would you get those points? You would do it. You would, yeah, that's why I told you to draw the thing first. Draw it first, and then you just have to put your thing up, move quadrant to midpoint. Find out it's called ID point. Well, I'll show you how to do that next week. But yeah, from your AutoCAD drawing, you can put a circle in here and find the center of the circle, right? Look, it'll tell you where the center X and Y is. So if you move that point to 0, 0, you can just get all this. Maybe we will do that next week. Well, yeah, I mean, it used to be a manufacturing engineer would do it, but now it's so coded into each machine, like like you can use Fusion and say, give me the tool path, and it'll do it. So yeah, so they've got it now. They've got it coded in. So they keep taking away our professions, right? There used to be a profession called drawing it. Now we don't draw it anymore. We model it. And now we're not even modeling it anymore with Fusion. They took away that job too. Now it's specify it. Fortunately, Fusion isn't quite good enough yet to be as good as a person, but they're working on it, and they will get there. There is no doubt they'll get there. So yeah, there is a profession. Manufacturing engineers do that. They create the tool paths and everything, and there's still stuff to do. You want to set how fast this is turning, how fast you're moving, whether you're turning clockwise or counterclockwise, what actual tool are you using. So there's still work to be done in manufacturing as a manufacturing engineer or manufacturing technician. But you're going to get the rudiments of it here. And you can imagine, well, let me just copy this thing. There, now I know the center point to put that on. Right? Right? And then I can copy it. And let's say I just want to move just far enough. Well, I'll move all the way out to here to get past it, right? Well, there's your next center point. There's your next one. So yes, we're going to get very good at it. Isn't that cool? I love it. Okay. Anyway, I'm going to go ahead and stop the recording.